Imagine writing, I don't know, millions of lines of perfect, bug-free C++ to govern a 6-axis robotic arm.
Right. A massive undertaking.
Exactly. You compile it, you flash it to the controller, and you turn it on, and it operates flawlessly. It's doing this highly specific task with, like, sub-millimeter precision.
Just exactly what it was programmed to do in a closed loop.
Right. But then, say 10 minutes later, an autonomous transport vehicle that you've never seen before, manufactured by a completely different company, just rolls into your robot's workspace.
Which is a complete variable injection.
Totally. It hands your robotic arm a completely foreign tool, transmits a semantic request to collaborate on assembling a product you never programmed it for, and just expects your robot to adapt its kinematics on the fly.
Which breaks every rule of traditional deterministic engineering.
Exactly.
Yeah.
And the crazy part is, your perfectly engineered, rigidly defined deterministic system actually evaluates the request, shifts its own internal architecture, and says yes.
It's wild to even think about, is that you just can't hard-code predictability when machines are interacting in, well, unpredictable environments. So CESs, which stands for Software Platform Embedded Systems, it gives engineers a framework to actually manage that chaos in real time.
Right, and for those of you following embedded systems, you know the original CES methodology is pretty well known. It was great for classical static systems with fixed boundaries.
Exactly, where you knew the inputs and the environment.
Yeah, exactly. But the new research focuses on CES, collaborative embedded systems, which dynamically form collaborative system groups, or CSGs, at runtime.
Right, so the shift is fundamentally about moving from a closed world to an open one. Think of it like a spontaneous basketball pickup game. You don't know who is going to show up to the court. Right.
Right, you don't know their skills or what shoes they're wearing.
Exactly, but you still need to run complex plays together instantly.
But in a pickup game, humans have intuition to figure that out, right? Machines don't really have that. So how does CES actually replace human intuition mathematically to form these groups?
Well, let's look at the vehicle platooning use case from the sources to see the mechanics of that.
Yeah.
So you have a 4-car platoon drafting on the highway in tight formation to, reduce air resistance and save fuel.
Okay, making sense so far.
Then a 5th car, let's call it Car E, wants to join. Under the CES framework, Car E doesn't just broadcast a basic let me in signal. It actually initiates a structured negotiation of soft goals.
Oh, so instead of just, looking for an open slot, Car E is basically establishing a behavioral contract.
Yeah, that's a great way to put it. It starts by aligning on an optimal cruising speed. Then the system actually assigns roles.
Wait, roles? Like it tells the car what to do?
Yes, Car E must actively accept the follower role, and that requires a physical handover of control decisions, meaning it actually relinquishes its own acceleration and braking limits to the lead vehicle of the platoon.
Wow, okay, but wait. What if Car E is built by a completely different manufacturer? Like, say the platoon uses LiDAR, but Car E relies heavily on optical cameras.
Right, the hardware heterogeneity problem.
Yeah. How does a framework handle that level of difference without crashing the moment they try to sync up?
And that is the main breakthrough of CES. Traditional programming fails here because you simply cannot write an if-then statement for every possible sensor combination from competitors. It's just impossible.
There are just too many variables out there.
Exactly. So instead, CES models collaboration functions and flexible spatial patterns using tools like traffic sequence charts or TSCs.
I've actually seen TSCs referenced in the papers, but how do they function at runtime? Are they just like visual diagrams of where the cars should be?
Not at all. They are rigorous mathematical models. A TSC doesn't care whether you use LiDAR or a camera. It just defines the boundaries of safe interaction.
So like maintaining a 2.5-second gap based on current velocity.
Spot on. As long as Car E's internal software can verify that it meets the TSC's behavioral boundary, the platoon accepts it.
Oh, wow. So it abstracts away the hardware entirely. It essentially says, I don't care how your sensors see the car in front of you, just mathematically prove you can react within this exact microsecond window.
Exactly. By modeling structures and behaviors rather than static code, the system architecture can dynamically adjust its interfaces.
That's incredible.
It really is. It reconfigures itself based on what the group needs in that exact millisecond, whether a new car joins or, say, a sudden rainstorm changes the road conditions.
Right. So to summarize the research for everyone listening, the CES methodology shows that the future of automation isn't just about making one machine incredibly smart.
Right. It is about establishing robust behavioral models. So diverse machines can trust and coordinate instantly, regardless of who built them.
So our mission for this deep dive is to decode the leap from traditional model-based systems engineering MBSE to a radical new paradigm called advanced systems engineering, or ASE.
Because we have to move past the high-level theory. We need to get straight into the metal and the math.
Exactly. We are going to dig into the exact computational mechanisms, the real-time safety protocols, and the mathematical modeling required to make dynamically formed networks of cyber-physical systems a reality.
Let's start with the foundational leap the text outlines. We are moving from classical embedded systems to collaborative embedded systems, or CES.
And these CES dynamically form what the text calls collaborative system groups, right? CSGs.
Right. And the bedrock they use to manage this is the SB methodology software platform embedded systems. But they had to heavily modify it.
Because SBS was originally designed for closed systems, right?
Exactly. It was built to master the complexity of single monolithic embedded systems. It is fundamentally a viewpoint-based engineering approach.
Break that down for us a bit.
Well, if you look at classical SPE, you divide the engineering process into 4 distinct viewpoints. You've got the requirements viewpoint, the functional viewpoint, the logical architecture, and the technical architecture.
Okay, so at the functional level, you are defining what the system does, like, say, an active braking function independent of the hardware.
Right, independent of the hardware. Then you map that to the logical viewpoint, which defines the actual software components. And finally, you move to the technical viewpoint, which maps the software to the physical electronic control units, the ECUs.
Which relies on, like, extreme mathematical precision in defining the interfaces between these decomposed layers.
Yes, but the CrESt project hit a massive wall with this.
Because classical SESBI assumes you know everything up front.
Exactly. It assumes all these viewpoints can be fully defined and just frozen at design time.
Right, because in a closed system, your technical architecture doesn't suddenly change on a random Tuesday afternoon.
No, it's static.
But in a collaborative system group, your system is suddenly forced to interface with a logical and technical architecture that literally didn't exist when you compiled your code.
It's a nightmare for a traditional systems engineer.
It's like moving from building a monolithic software kernel to a highly distributed microservices architecture, but doing it in the physical world with moving metal. So how does the extended SPE methodology actually handle this dynamic binding computationally?
It introduces this crucial concept of the open world assumption.
The open world assumption, okay.
In traditional MBSE, you operate under a closed world assumption. Basically, anything not explicitly modeled is assumed to be false or non-existent.
If it's not in the code, it doesn't exist.
Right. But the open world assumption forces the system to operate under the premise that its knowledge is inherently incomplete.
Oh, wow. So the machine knows it doesn't know everything.
Exactly.
Yeah.
To achieve this, the CSP's methodology had to be extended to include formal collaboration models and context models.
So when a collaborative embedded system, a CES, encounters another machine, they don't just, like, exchange raw data packets?
No, they exchange semantic models of their capabilities. It is a highly structured handshake.
So System A transmits a formal specification of its functional interfaces. It's essentially saying, I have the computational capability to process computer vision data, and I require a minimum latency of 10 milliseconds.
And then System B has to evaluate that requirement against its own current state.
So as an engineer, you are no longer just writing the internal logic of the machine. You are writing the meta logic that allows the machine to evaluate its own state, evaluate an external system's proposed state, and mathematically prove that combining those two states won't violate any core system invariance.
You are engineering a node that continuously redraws its own boundaries. You're engineering a system that has to generate a runtime architectural model of a group that literally didn't exist a minute ago.
That is wild.
It has to instantiate new logical connections, allocate computational resources, and agree on shared goals without a central server orchestrating the transaction.
So it's entirely decentralized negotiation.
Entirely.
Okay, this decentralized negotiation sounds elegant in theory, but semantic handshakes in a vacuum don't really reflect physical reality. Let's force this theoretical framework into a high-stakes, high-speed physical environment.
I like where this is going.
Yeah, the text details several massive industrial use cases to stress test this architecture, and I think the most visceral one is cooperative automation on the highway specifically, vehicle platooning.
Platooning is the ultimate crucible for the open world assumption. I mean, you have massive kinetic energy, split-second latency requirements, and an environment governed by unpredictable physics and, well, human behavior.
To set the baseline here for the listener, we aren't talking about standard adaptive cruise control. An engineer listening to this knows how ACC works.
Right, standard ACC is a local PID controller taking inputs from a forward-facing millimeter wave radar.
Exactly. It calculates the delta in velocity and distance and actuates the throttle or brakes to maintain a time gap. It is a strictly local, reactive, closed-loop system.
But the text contrasts this isolated system with collaborative adaptive cruise control, or CACC.
CACC. And this uses vehicle-to-vehicle, V2V communication to physically couple multiple vehicles into a platoon.
Which becomes our collaborative system group.
Right. And the aerodynamic benefits are massive. Fuel consumption drops, highway throughput skyrockets. But mechanistically, how do these vehicles actually transition from isolated actors to a synchronized CSG?
Well, it requires a fundamental shift from reactive control to predictive cooperative control.
Okay, so they aren't just reacting to the car in front of them anymore.
Right. The vehicles are no longer just bouncing radar off the bumper in front of them. They are utilizing V2V protocols, typically dedicated short-range communications, DSRC, or cellular V2X.
And they are broadcasting state vectors at incredibly high frequencies.
Exactly. And a state vector isn't just, I am here.
It's much deeper than that.
It's a multi-dimensional matrix containing exact GPS coordinates, current velocity, multi-axis acceleration, yaw rate, steering angle, and crucially intent.
Intent. So the lead vehicle is transmitting its calculated braking trajectory before its physical brake calipers even touch the rotors.
Yes, which entirely eliminates the latency cascade you get in a human traffic jam.
Right, where Vehicle 5 doesn't brake until Vehicle 4's brake lights turn on.
Exactly.
But wait, this requires flawless clock synchronization, doesn't it? If the internal clock of the third truck in the platoon is drifting by even a few milliseconds compared to the lead truck, the state vector data is effectively corrupted.
That is a huge issue, yes.
Because the third truck calculates the lead truck's position based on a timestamp that doesn't align with its own perception of physical reality.
Precisely. And this is where the extended CESs functional modeling is applied. The CACC electronic control unit inside the car has to integrate its local goals with the overarching goals of the CSG.
How does it divide those goals?
The architecture separates the tactical layer from the operational layer.
Okay, the tactical layer, what does that handle?
The tactical layer negotiates the high-level goals. So, sharing a destination, agreeing on a cruising speed, and mathematically minimizing the fuel consumption polynomial for the entire group.
So it's doing the broad strategy.
Right. It handles the discrete life cycle phases of the platoon, the protocols for creating it, verifying the security certificates of a vehicle trying to join, and safely dissolving it.
And then the operational layer?
The operational layer handles the continuous time physics. It takes those state vectors and feeds them into a model predictive control algorithm to actuate the steering and brakes in real time.
Let's push back on this, though, because a highway is the absolute definition of an open context. It is not a deterministic, closed test track.
Not at all.
So what happens when this beautifully synchronized, digitally bound CSG encounters a variable it fundamentally cannot communicate with?
The edge cases.
Right. Let's say we have a platoon of 5 digitally connected trucks cruising at 100 kilometers per hour with a 3-meter gap between them. Suddenly, a totally unconnected, human-driven sports car aggressively swerves into the middle of the formation to catch an exit.
A classic highway nightmare.
The local radar on truck 3 sees a mass of metal instantly appear in its braking zone.
This introduces a critical concept from the text: epistemic uncertainty.
Epistemic uncertainty. Meaning what exactly?
It arises purely from a lack of knowledge about the environment. The system cannot ping the sports car for a state vector. It cannot read the human driver's intent.
Right, because it's a closed legacy vehicle. In a classical isolated ACC system, the response is simple and highly dangerous, right? Truck 3 detects a massive distance violation and triggers a maximum G emergency stop.
And truck 4 and 5, reacting purely to truck 3, also slam on the brakes.
Which, at best, causes a phantom traffic jam.
And at worst, causes a multi-vehicle collision because the aerodynamic drafting gap is way too small for standard reaction times.
So how does the collaborative architecture computationally solve a problem it literally doesn't have the data to understand?
By executing a real-time architectural reconfiguration based on goal-driven strategy exploration.
Wow, okay. Break that down. What happens in that millisecond?
The instant the local radar on truck 3 detects the unauthorized intrusion, it doesn't just actuate its own brakes. It flags a severe invariant violation to the entire CSG.
So it yells to the whole group, something is wrong.
Exactly. The platoon's distributed tactical layer instantly evaluates its collaborative models. It recognizes that maintaining the current CSG topology is no longer viable or safe.
So it's running a massive optimization problem in milliseconds. It has to decide, do we all break? Do we
Yeah.
dissolve the entire platoon and revert to isolated ACC mode?
Exactly. And because they are sharing a collaborative context model, the computational load can be distributed among the trucks.
What's the optimal strategy in that scenario?
Well, the system might calculate that the optimal strategy to preserve kinetic energy and safety is a controlled split.
A split. So truck 3 gracefully decelerates to open a safe following distance for the erratic human driver, effectively becoming the new lead vehicle for a secondary platoon.
Exactly. And truck 1 and 2 maintain their speed and configuration as the primary platoon.
They have dynamically dissolved one CSG and instantiated 2 new ones, adjusting their control parameters on the fly, all without any human intervention.
That is the power of the ASE paradigm.
That is just staggering. The system isn't just reacting to physics, it is rewriting its own network topology to change how it reacts to physics.
It's meta control.
Exactly. But platooning, as complex as it is, still operates on a fundamentally linear one-dimensional plane. You are moving forward on a highway. The goals are relatively simple. Don't crash, save fuel, maintain speed.
Right. It's complex, but bounded physically.
What happens when we take this open world assumption and move it into a three-dimensional, nonlinear environment where the goals aren't just maintain distance, but build a complex physical product?
That forces a total architectural shift.
Which transitions our deep dive from the highway to the adaptable factory floor industry 4.0.
The transition from classical manufacturing to the adaptable factory represents a massive leap in spatial and logical complexity.
Because on the highway, the physical topology sort of dictates the flow.
Right, but in an adaptable factory, the logical goals dictate the physical topology.
The text highlights the shift away from rigid mass production. We are talking about completely abandoning the fixed belt conveyor and the static assembly line.
The engineering target is the fully adaptable factory designed for lot size 1 customization.
Lot size 1. And the specific example in the source is the assembly of a quadricopter. Now, any engineer listening knows what goes into a drone, but the challenge here is that every single order coming into the factory might specify a different payload, a different battery chemistry, a different rotor configuration.
High variability is the baseline requirement. It's not the exception anymore.
So to handle that extreme variability without halting production to physically retool the line, the factory architecture abandons the monolithic structure.
Yes, it relies entirely on flexible production modules. These are our individual collaborative embedded systems.
So you have a robotic manipulator that isn't hard-coded to do just one thing. It has an automatic tool changer and a library of kinematic models.
Exactly. It can weld on one cycle, inspect with a vision system on the next, and then apply adhesive on the third.
But the real paradigm shift is how materials actually move between these flexible nodes, right? If you remove the conveyor belt, you remove the physical manifestation of the schedule.
You're removing the track.
Right. You replace it with autonomous transport robots, or ATRs.
These are mobile CES, navigating the factory floor, dynamically routing materials between the production stations based on real-time demand.
Which creates a highly volatile, highly dynamic collaborative system group. You have stationary production modules and mobile transport modules that must continuously form temporary CSGs to hand off materials and execute production steps.
It's a constant dance of temporary alliances.
But mechanistically, how do they coordinate this? If there is no central master controller explicitly commanding ATR number 4 to go to Station B, how does anything actually get built?
It's a great question.
How do you prevent 5 different transport robots from simultaneously deciding they need to pick up the same battery pack, converging on a single aisle, and causing a massive deadlock?
This requires a fully decentralized control architecture utilizing advanced communication protocols.
Because in a traditional factory, you have a manufacturing execution system, an MES.
Right, acting as a dictator via a client-server architecture. It pulls every PLC, calculates the global state, and pushes deterministic commands down.
You do this, you do that.
Exactly. But the CrESt text suggests that true adaptability requires the MES to step back. It acts more as a broker or an observer, while the edge devices use goal-based strategies and peer-to-peer protocols.
Are they using something like a publish-subscribe protocol, like MQTT or DDS?
Yes, Data Distribution Service, DDS, is highly relevant here because it allows for real-time, decentralized data exchange. But the actual decision-making relies on negotiation protocols, often resembling a contract net protocol.
Contract net protocol. Let's look at the computational mechanism of that.
Okay, so imagine a production module finishes a subassembly.
Right.
It publishes a multicast request to the network. I have a completed subassembly at location X that requires transport to a testing station. It acts as a manager broadcasting a task.
So it's essentially an automated auction system on the factory floor.
Exactly. The available autonomous transport robots act as contractors. They receive the broadcast.
And then what? Do they just all rush there?
No, each ATR runs a local cost function. It calculates its current distance to location X, its current battery level, and the computational weight of path planning algorithms like A-star or D-star required to navigate the current factory traffic to get there.
So it generates a bid based on its own unique context.
Exactly, say an estimated time of arrival and energy cost.
Yeah.
And it sends that bid back to the production module.
And the module evaluates the bids, selects the optimal ATR, and awarded the contract.
Right.
And once the contract is awarded, those two specific machines dynamically form a temporary collaborative system group.
They establish a secure, localized communication channel, execute the physical handoff, and then immediately dissolve the CSG so the ATR can move on to the next task.
It is a completely self-organizing topology based on decentralized bid-based dispatching. That's incredible.
And this solved the deadlock issue you mentioned earlier.
Because the routing logic isn't hard-coded into a central server.
Exactly. The ATRs are continuously recalculating their paths based on the real-time location of other ATRs. If an aisle is blocked, the cost function for that route spikes, and the ATR naturally bids on different jobs or calculates a detour.
The factory handles the variability of the product by varying its own internal architecture at runtime.
It is the ultimate expression of flexibility.
Wait. As an engineer, my entire job is deterministic safety.
Oh, here we go. Yes.
Right. If I am designing a system using traditional standards like ISO 26262 for functional safety in vehicles, or the European Machinery Directive for industrial robotics, my methodology relies entirely on a priori knowledge.
Absolutely.
I write a definitive fault tree analysis. I calculate the exact failure rates of every single microswitch. I map every possible state the machine can be in. I prove that none of those states violate safety parameters, and I get a certification stamp before the machine is ever powered on.
The classic waterfall safety model.
But you just described a factory where the logical state and the physical layout of the machines are literally unpredictable at design time. My traditional ISO standards are utterly useless here. I can't write a deterministic fault tree for an open context.
You can't.
So how am I supposed to legally, mathematically, or ethically certify this machine?
You have hit on the exact engineering crisis that birthed the concept of advanced systems engineering. You cannot certify a shape-shifting network using static monolithic safety cases.
So what's the alternative?
The text proposes a radical solution: dynamic safety certification utilizing modular safety cases and contract-based design.
Contract-based design. So we are treating safety guarantees the same way we treat the task auction we just talked about.
Precisely. Instead of writing one massive, unyielding safety document for the entire factory, you engineer modular safety cases that are bound to the specific capabilities of the individual CES.
Okay, so in contract-based design, every functional component has a formal contract consisting of assumptions and guarantees.
Right. The system says, assuming my environment meets condition X, I guarantee my output will meet condition Y.
So it's based strictly on preconditions, postconditions, and invariants.
Yes. And when these machines attempt to form a collaborative system group at runtime, they don't just exchange data, they computationally evaluate each other's safety contracts.
So if an ATR wants to interface with a robotic arm, the arm's safety module queries the ATR.
And if the combined assumptions and guarantees of both machines satisfy the overarching safety requirements of the proposed configuration, the collaboration is approved.
So the safety certification is mathematically proven at runtime, literally milliseconds before the physical interaction occurs.
It's dynamic certification in the purest sense.
But hold on, that mathematical proof is only valid if the data feeding it is absolute. And we know that in modern systems, especially with digitalization, we aren't just using deterministic sensors like encoders or limit switches anymore. We are using artificial intelligence.
Which brings us to a massive challenge outlined in the text.
Right, how these systems understand uncertainty. The text introduces the Eureka ontology. Eureka stands for European Project on Dealing with Uncertainty in Collaborative Systems.
And it strictly separates epistemic uncertainty, which we discussed earlier, with the unpredictable human driver from data-driven uncertainty.
This distinction is critical for the digitalization engineer. Explain data-driven uncertainty.
Data-driven uncertainty is an inherent byproduct of integrating machine learning. The text specifically addresses data-driven components, or DDCs.
These are your neural networks acting as advanced sensors.
Think of a convolutional neural network on an autonomous transport robot processing LiDAR point clouds and video feeds to recognize a human worker versus a stationary pillar.
And the problem is that a neural network is effectively a black box.
Exactly.
It doesn't run a hard-coded if-then loop. It learned its behavior by minimizing a loss function across millions of training images. You cannot mathematically guarantee using traditional formal methods that the network won't misclassify a shadow or a weird reflection.
It introduces severe data-driven uncertainty into our supposedly rigorous runtime safety contracts.
Which means you cannot directly link a data-driven component to a safety-critical actuator. If you do, your entire mathematical safety proof collapses.
It's a house of cards at that point.
So how do you trust it? I mean, I can't certify the black docs.
You don't try to certify the black box, you certify a deterministic monitor that bounds the black box.
Bounding the box,
The
okay.
text proposes equipping every DDC with what it calls a wrapper. This is conceptually similar to the simplex architecture used in fault-tolerant control systems.
Oh, simplex, okay.
The wrapper acts as an absolute deterministic monitoring layer that evaluates the output of the AI before that output is ever allowed to influence the physical system.
So it's essentially a Kalman filter for confidence. The wrapper isn't looking at the object on the factory floor, it's looking at the mathematical variance of the neural network's output.
That is an excellent translation of the mechanism.
It translates that opaque statistical variance into a strict, bounded safety metric, like a binary safe and safe token, or a specific confidence interval that the deterministic PLC can actually read and trust.
Right. So the neural network might output, I see an object, classification, human, confidence, 72%.
And then what does the wrapper do?
The deterministic wrapper takes that vector, references its internal safety rules, and determines that 72% confidence on a human classification requires a fallback state.
It intercepts it.
It intercepts the AI's intended trajectory command and instead outputs a mathematically proven safe command to the loader controllers, reduce velocity to 0.
So as the engineer, you must completely shift your mindset. You are no longer trying to engineer an AI that never makes a mistake, which is statistically impossible.
Completely impossible.
You are engineering the system's strict self-awareness of its own statistical limitations. You are writing the deterministic boundary conditions that allow the AI to safely express doubt.
That's a beautiful way to put it, safely expressing doubt.
Because if the wrapper flags the uncertainty as too high, the runtime safety contract we talked about earlier is instantly voided, and the CSG gracefully degrades to a known safe state.
And crucially, that gracefully degraded state is pre-calculated and mathematically proven. This fusion of non-deterministic data-driven components bounded by deterministic model-based wrappers is the hallmark of advanced systems engineering.
But this raises an enormous practical question. If we are relying on these dynamic runtime safety contracts and wrappers bounding AI and bid-based task dispatching, we cannot possibly test every permutation of these interactions in the physical world.
No, it would take a billion years.
Right, to physically test every way a factory could reconfigure itself, or every variable a vehicle platoon might encounter. If we can't test it physically, how do we validate it before deployment?
This moves our deep dive from physical metal into the digital realm. We are talking about testing the untestable using digital twins, ontologies, and co-simulation.
Because testing open context collaborative systems requires a total reinvention of simulation architecture. You cannot simulate an isolated machine anymore. You have to simulate the entire digital ecosystem, the communication latency, the physics, and the emergent behaviors all at once.
And the text traces the progression of simulation methods that engineers are familiar with. You've got model in the loop, MIL, where you test the control algorithms in pure math.
Then software in the loop, SIL, where you compile that math into the actual C++ code and run it on a virtual machine.
Right. And then hardware in the loop, HIL, where you take the physical electronic control unit, the real silicon, and trick its inputs into thinking it's connected to a real machine.
But to handle CSGs, the text pushes way past HIL and introduces digital twins DTs. And it defines them not just as like 3D CAD models, but as executable models.
This is a huge distinction.
Yeah.
An executable digital twin is a living computational shadow of the physical system.
So it doesn't just look like the machine.
No, it runs the exact same control logic, it ingests the exact same live sensor telemetry, and operates in real time alongside its physical counterpart.
Which allows the system to evaluate goals at the strategic, tactical, and operational levels simultaneously.
Exactly. You can utilize the digital twin to run predictive simulations faster than real time.
So if the factory floor encounters a bottleneck, the central system can just instantiate 1,000 instances of the digital twin.
Run a Monte Carlo simulation on different routing strategies,
Find the optimal topology.
and push that configuration down to the physical ATRs instantly.
That's insane. And to prove this actually works, the CrESt project conducted this fascinating co-simulation experiment. They wanted to test the collaborative platooning software we discussed earlier.
Right, the CACC software.
But obviously, taking unproven dynamic CC software and flashing it to a fleet of 40-ton trucks on the Autobahn is ethically and legally impossible.
A total non-starter.
So they utilized a co-simulation framework called Feral, F-E-R-A-L, and they combined Feral with physical 1.0 scale model cars specifically, and Kai overdrive cars.
This is an absolute masterclass in bridging discrete event simulation with continuous time physics.
Tell us about Feral.
Feral is a framework specifically designed to couple different domain-specific simulators together.
Let's break down exactly how this works mechanically in the experiment. They put the actual production-ready CCC software onto the microcontrollers of the physical 1.0 scale toy cars.
Right. Real software, small hardware.
The real physical car is driving on a real track in a laboratory. It is dealing with real physical latency, real tire slip, real motor torque, but it is communicating its state vectors into the Feral network.
And inside the Feral simulation, there is a massive virtual highway environment running a traffic simulator like Sumo.
So the virtual trucks in the simulation receive the physical toy car's state vector, and they transmit their virtual state vectors back to the toy car.
And the computational magic here is the clock synchronization.
Why is that the magic part?
Because Feral has to perfectly synchronize the timestamps of the physical network packets originating from the Kaya car with the virtual time of the software simulation.
Oh, wow. So if the physical car encounters a slight bump and its wheel slips, changing its velocity for 10 milliseconds, that physical reality is instantly mapped into the virtual simulation, and the virtual platoon reacts.
Exactly. The physical car truly believes it is driving in a high-speed platoon with 40-ton trucks.
It allows engineers to inject massive epistemic uncertainty, like, spawning a virtual crashed car right in front of the physical toy car, and watch how the real silicon and real physical actuators respond without risking any human life.
It bridges the gap perfectly.
But for the digital twin or the co-simulation to work, the machine has to have a way to translate raw data like LiDAR point clouds or network packets into a semantic understanding of its environment.
Right. The machine has to actually understand what it's looking at.
How does a machine automatically generate a model of its ever-changing context so it can actually run these internal simulations?
It achieves this through knowledge graphs and ontologies. The text details the use of tools like SparkEL and Web Ontology Language, ABL.
Okay, let's pause and look at the actual data structures here.
Yeah.
Because when I hear ontologies and SparkEL, my eyes just glaze over a bit. How does this actually work in the machine's brain?
Well, think of an ontology as a highly structured, machine-readable semantic web. It doesn't just define isolated variables. It mathematically defines the relationships and constraints between entities.
Give me an example.
A conventional database might have a simple table for robots and a table for tools. An ontology, however, defines that robot A is capable of wielding tool B, but only if payload is less than 50 kilograms.
So it's mapping the physical world into a massive interconnected graph of logic.
Exactly. The system builds a feature model of its own capabilities. It then cross-references this internal feature model against a variability context model.
What's a variability context model?
It's a formal representation of all the parameters in its open environment that could possibly change. By continuously fusing its live sensor data with these models, it updates a live knowledge graph.
Let's apply this to the factory floor just to ground it. An autonomous transport robot doesn't just see a cluster of pixels on its camera and a bounding box from its neural net.
No, it maps that bounding box into its knowledge graph.
The graph queries the ontology using SparkEL, which is a semantic query language, and deduces. This bounding box is an entity of class human worker. Rule set dictates human worker has unpredictable trajectory. Therefore, my safety wrapper requires a speed reduction to 1 meter per second.
Exactly. It is translating raw photons into executable logic.
And having this highly structured live knowledge graph unlocks the final and I think most advanced capability detailed in the text, Online experiment-driven learning.
This is where it gets incredibly sci-fi, but it's very real. Because the system deeply understands its context through the ontology, it can safely conduct live statistical experiments on itself to optimize its performance.
The text specifically cites the use of factorial ANOVA analysis of variance applied in real time.
Yes.
Factorial ANOVA. So the machine is essentially running a continuous multivariable A/B test on its own control parameters.
Yes, but with mathematical rigor to account for compounding variables. In a closed system, you tune your PID loops at the factory and never touch them again.
Right, you lock it down.
But in an open context, the optimum parameter changes based on the environment. The system looks at its current performance metrics, say, the energy efficiency of the platoon. It slightly tweaks an independent variable, like the aerodynamic following distance, within the strict boundaries of its safety wrapper.
And then?
It then uses factorial ANOVA to analyze the dependent variable, the actual fuel consumed, while isolating confounding factors like wind speed or road incline.
It evaluates if the tweak had a statistically significant positive effect. If the p-value indicates the improvement is real and not just noise, the system permanently adopts the new parameter.
It is continuously experimenting, learning, and rewriting its own operational strategies based on the reality of its open context.
If you step back and look at the computational architecture required to achieve this, it is just breathtaking. The machine is continuously ingesting high-frequency telemetry, filtering it through AI wrappers, mapping it into a semantic knowledge graph via OWL ontologies, executing digital twin simulations of alternative realities, negotiating dynamic safety contracts via bid-based protocols, and using factorial ANOVA to optimize its own source code.
All executed in milliseconds.
This is why edge computing and ultra-low latency networks like 5G and time-sensitive networking TSN are not just buzzwords. They are the fundamental physical prerequisites for collaborative embedded systems to even exist.
Without that infrastructure, the whole paradigm collapses.
Which brings all these threads together perfectly. We have completely dismantled the traditional engineering approach. We are no longer building isolated, deterministic machines. This leads us to the culmination of the CrESt project and the final section of our deep dive, the paradigm shift to advanced systems engineering, or AS.
ASE is the formal acknowledgement that you cannot build the cyber-physical ecosystems of the future using the methodologies of the past.
The text defines ASE as the necessary paradigm for the agile, evolutionary, and quality-aware development of autonomous networks.
And it lays out 3 core tenets of ASE that every engineer really needs to internalize. First is absolute front-loading.
Front-loading meaning what?
It means shifting the vast majority of the engineering effort, verification, and validation to the earliest phases of development using virtual digital artifacts.
You are no longer cutting metal, building a physical prototype, and putting it on a shaker table to see if it breaks?
No, you are exhaustively testing the executable digital twins in feral co-simulations, simulating millions of open context encounters before you ever order a physical PCB.
Wow. And the second tenet?
The second tenet is the complete merging of model-driven and data-driven approaches. We discussed this with the AI wrappers. You must combine the rigorous, deterministic mathematical proofs of MBSE with the highly adaptable statistical power of machine learning.
You need the neural network to handle the messy reality of the physical world, and you need the deterministic model to mathematically guarantee it doesn't kill anyone.
Exactly. And the third tenet is perhaps the most disruptive to traditional manufacturing, erasing the line between development and operation.
We are talking about continuous evolution DevOps for physical physics. An industrial robot or an autonomous vehicle is never truly finished.
Right. It is a dynamic platform that is constantly downloading new operational strategies, updating its ontologies, and refining its parameters based on the collective factorial ANOVA learning of the entire global fleet.
To enable this massive shift, the foundational engineering language has to change, right? The text notes that the industry currently relies heavily on CSML systems modeling language.
But SysML is fundamentally a descriptive language. It lacks rigorous formal semantics. If you draw a SysML state machine diagram, 2 different software tools or 2 different engineers might interpret the exact execution timing completely differently.
Which is a catastrophic liability if you are trying to write a mathematically proven runtime safety contract. Ambiguity is the enemy of safety.
Exactly. This is why the extension of the SysML methodology is so critical. SPIS provides the mathematical, formal foundation that SysML lacks.
So when you define a logical interface between two systems using CPIS, it relies on formal specification languages.
It means exactly the same thing mathematically to the compiler, to the verification tool, and to the machine executing the code. It provides the strict, system-centric granularity required to manage infinite complexity.
So advanced systems engineering represents a complete philosophical and methodological paradigm shift. We are moving from engineering purely mechanical, isolated objects to engineering networked, information-centric digital ecosystems.
Because of the integration of open-world assumptions, ontologies, and online experiment-driven learning, the software essentially continues to optimize and write itself during operation.
That is the ultimate conclusion of the CrESt project. As an engineer, you are no longer designing the exact behavior of the machine. You are designing the genetic code, the semantic negotiation protocols, and the absolute safety boundaries.
The system's exact operational behavior will dynamically evolve based on the physical environment it encounters.
The concept of a finished product is officially dead. Think about the gravity of that. As an engineer, you are no longer building a static machine. You are birthing an evolving node in a larger digital ecosystem.
That's a profound way to look at it.
For you, the listener, studying the bleeding edge of digitalization, this is the ultimate takeaway. Your value in the ASE era does not lie in defining rigid step-by-step logic loops. Your value lies in designing flexible, resilient, computationally self-aware architectures.
You are building the mathematical frameworks that allow a system to learn, to negotiate securely with completely unknown partners, and to remain absolutely safe in a physical world that you cannot predict.
You are no longer just engineering machines. You are engineering the foundational architecture of autonomy.
It's a massive responsibility.
Let's do a highly technical recap of the deep dive we just took. We started with the monumental leap from classical embedded systems to collaborative system groups, replacing the closed world assumption with the open world assumption, and utilizing the formally grounded CESs methodology to handle dynamic semantic handshakes.
We stress tested this on the highway with vehicle platooning.
Diving into the V2V state vectors, clock synchronization, and how tactical distributed layers handle epistemic uncertainty by recalculating their kinetic topology in milliseconds.
Then we transitioned to the 3D complexity of the Industry 4.0 adaptable factory.
Where autonomous transport robots replace conveyor belts using decentralized, bid-based contract net protocols and A-star path planning to self-organize. We confronted the nightmare of open context safety, utilizing modular contract-based design to mathematically prove safety at runtime, and we broke down how deterministic simplex wrappers bound the statistical variance of data-driven neural networks.
We explored how to test this via feral co-simulation,
Synchronizing virtual clocks with real-world latency, and we mapped raw photons into logic using adaptable ontologies, spark-hole queries, and live knowledge graphs, allowing the system to self-optimize using real-time factorial ANOVA. And finally, we arrived at advanced systems engineering, the new paradigm of front-loaded continuous DevOps for cyber-physical ecosystems.
It's a rigorous, mathematically sound roadmap for the next century of engineering.
It absolutely is. But I want to leave you with one final, slightly provocative thought to mull over. We talked at the very beginning about dropping your perfectly designed machine into a dynamic environment. If we are successfully executing advanced systems engineering, if these machines are using digital twins to continuously simulate alternative realities faster than real time, if they are using complex ontologies to perfectly map the semantics of their world, and if they are using continuous statistical analysis to optimize their own behavior and form autonomous networks without our explicit instruction, at what point does this network of machines stop being a rigid infrastructure that we control and start becoming an independent, self-governing digital ecosystem that we merely participate in? Think about that the next time you draw a boundary box around your system. Until next time, keep diving deep.